Good morning, dear students. My name is Ferhan Mazher, and the subject today we are studying is Cambridge O Levels Physics 5054. Today we are working on some, you say, practice questions which are about the space physics, and they have been issued or published by the Cambridge. Uh, so this booklet which I am using, the purpose of this booklet is to provide additional practice questions and answers for the space physics topic, which has been introduced to Cambridge O Levels Physics 5054 for first assessment in 2023. Practice questions have been provided to exemplify a range of a range of types of questions which could appear in examinations. So let's start today's. So the first question coming up, I can show you the booklet. This is that booklet, and this has been issued by the Cambridge. So we are going to do some paper 2 questions today in this video. The paper 1 questions I have already done. I have made a video on MCQs, and I have yeah. So I have put that video. You can watch that video, which has MCQs regarding the space physics. Today we are working on the structured questions, which are from the paper 2. These are example questions. Okay, so we are going to start today's work. So the first question coming up on your screen, and that question is okay. So the solar system contains the sun, planets, moons, asteroids, and comets. State the name of the planet closest to the sun. So you can remember the order of the planets. We have that mnemonic, which is my very educated mother just served us nachos. My very educated mother just served us nachos. From this, you can remember, okay. So it means Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. So the planet which is nearest to the sun, that is Mercury. Okay. So then the question number 1B part, describe the difference between a planet and a moon. You see, planet is a body which is orbiting around the sun, and moon is a solid body which is orbiting around planet. So let me show you, planet orbit around sun, moon orbit around our planet. So this is my answer. Question number 1C, part, state two differences between an asteroid and a comet. You see, asteroids are made of rocks and metals, whereas the comets, they are made of ice. The the orbit of the asteroids around the sun is circular, whereas the orbit of the comets around the sun is elliptical, and that elliptical is stretched. So let's have a look at what I have written. Okay. Question number 1C part. Comets have elliptical orbits, whereas the asteroids have circular orbits. Comets are made of ice, whereas asteroids are made of rocks and metals. Question number 1D part, he says the planet closest to the sun orbits, the planet closest to the sun is the Mercury, and he says the orbits the sun in 88 days. State two reasons why the Earth takes longer to orbit the sun than its planet and than this planet. You see, the Earth, its orbit is larger than the orbit of the Mercury, plus the the orbital speed of the Earth is slower. As the planets, you take a planet which is away from the sun, its orbital speed will be less. So the orbital speed of the Earth is less than the orbital speed of that planet, and the orbit of the Earth is larger than the orbit of that planet. So my answer is the Earth has slower orbital speed than the planet, and the second is Earth has larger orbit than the orbit of the planet. Okay, question number 1E, first part. He says, state the time taken State the time taken for light to travel from the sun to the earth. The uh, the the light takes 500 seconds to uh, reach from the sun to the earth. So it takes 500 seconds. So simple. It's just a number. You have to remember this. Okay. Then we have, he says, using your answer to E first part, calculate the distance from the sun to the earth, showing your work. You know, we know the speed of the light in the vacuum. That is 3 expo 8 meter per second. And we know that the earth, the light takes 500 seconds to come to go from the sun to the earth. So I know the speed of the light. I know how much time it takes to go from sun to the earth. So we can calculate the distance between the sun and the earth. The distance is equal to speed multiplied time. The speed is 3 expo 8 meter per second. And the time taken is 500 seconds. You simply multiply them, you get 1.5 expo 11 meter. So the distance between the earth and the sun is 1.5 expo 11 meters. So here we go. Question number 1 and its marking scheme is showing up on your screen. I have already checked my answers from the marking scheme. You can pause the video here and you can take your time with the marking scheme of the question number 1. Okay, so we are going to the next question. The next question is question number 2, A part. A year, a month, and a day can be defined in terms of motions of the earth, the moon, and the sun. Using these motions, complete the following sentences. A year is the time for. A year is the time in which the earth completes its orbit around the sun. A month is the time for. A month is the time in which the moon of the earth completes its orbit around the earth. A day is the time for. A day is the time in which the earth completes its complete spin around its own axis. So this is my answers. Okay, so let's have a look what I have written. A year is the time for the moon to complete its orbit around sun. A month is the time for moon to complete its orbit around earth. A day is time for earth to rotate once on its axis. Question number 2 is B part. He says Earth, Jupiter, and Saturn are 3 planets in the solar system. The table 2.1 gives information about these planets. And Earth, its orbital speed is 1.1 expo 5 kilometer per hour. Time for the orbit around the sun in years is 1 year. Jupiter, its orbital speed is 4.7 expo 4 kilometer per hour, and it takes 12 years to complete its orbit. And Saturn, its orbital speed is 3.5 expo 4 kilometer per hour, and it takes 29 years to orbit sun. Okay, so using the data from the table 2.1, calculate the average radius of the Saturn orbit around the sun. Give your answer in kilometers. It's a 3 marks question. Very simple, straightforward question. You know the orbital speed is equals to 2 pi r divided by time. The orbital speed of the Saturn is given, that is 3.5 expo 4 kilometer per hour. And the time is also given, it takes 29 years. Because in the speed, the time is in hours. So we will convert 29 years into hours. How you convert that? You will 29 multiply 365 multiply 24. So you will get the time in hours. And orbital speed is equal to 2 pi r divided by time. So I can calculate r, the radius of the orbit of the Saturn. So on your screen, this is showing up. Orbital speed is equal to 2 pi r divided by pi if I make r the subject of the formula. So the r will be equal to the orbital speed multiplied time divided by 2 pi. The orbital speed of the Saturn is 3.5 expo 4 multiply. The time I will take in hours, it takes 29 years to complete one orbit. So it will be 29 multiplied 365 multiplied 24 and divided by 2 pi. When you enter these values in your calculator, you will get 1.4 expo 9 kilometer. 1.4 expo 9 kilometer is the right answer, sir. Okay, question number 2, it's C part. He says figure 2.1 shows one alignment with the sun of Earth, Jupiter, and Saturn. Okay, so here you have the sun, here we have the Earth, Jupiter, Saturn, and in this direction, clockwise, they are rotating. In the figure 2.1, the three planets and the sun are in line. 29 years later, Saturn returns to the same position relative to the sun, but Earth and Jupiter are not in the same line. The Jupiter and the Earth, they both will be not together on the same line. Okay. Use data from the table 2.1 to explain why. Explain why. It's a 2 marks question. So you see the table which is this one. Okay. So we know that the Earth will complete its orbit in one year. Okay. So in 29 years, the Earth will be back to the same position, but the Jupiter, it will be it takes 12 years to complete its orbit. So in 29 years, it will be 12 divided by 29 multiply. So you will check. 29 divided by 12. You will do 29 divided by 12, and you will get how many cycles, revolutions it has completed. And in the same way, we know the Saturn, it is 29. It takes 29 years to complete. So 29 divided by 29. So Saturn will be back on the same position. But the Jupiter will have not done the same thing. Let me show you my answer. Okay. So in 29 years, Earth will complete 29 trips of its orbit, but the Jupiter will complete 29 divided by 12, because the Jupiter takes 12 years to complete one rotation around the sun. So it will complete 2.4 trips around its orbit. So that's why the Earth and the Jupiter will be no more in the same line in which they are shown in that diagram. So it's a little tricky question. Okay. Okay, the next question is, here we have, he says, complete the figure 2.2 to show the positions of the three planets exactly 6 years after the diagram. Okay, so this is their original condition. So for the Earth, you know, the Earth after 6 years will be back on the same position. So the Earth will be here on the same, the Earth will be back on the same position. So the Earth will be here. Okay. Then we will have Jupiter, because the Jupiter takes 29 years to complete. But in 6 years, how much it has completed? So 6 divided by 29 multiply 360. So you will get the angle of the, the Jupiter takes 12 years. So 6 divided by 12 multiply 360. So you will get 180 degree. So the Jupiter will be here. The Jupiter will be here. Okay, then we have that Saturn, and Saturn takes 29 years to complete one revolution. So in 6 years, it will be 6 by 29 multiply 360. So you will get 74 angles. So put a D here. So mark 74. 74 will be here somewhere. So the Jupiter, the Saturn, the last one, the Saturn will be here. Okay, the Saturn will be here. Here we will have this, because Saturn is here, so it will come here. So let me show you my answer, and I have also shown some working with it. Okay, so after 6 years, the Earth will be on the same position. You can see here, the Earth will be back here, because in 6 years, it would have completed 6 rotations. So it will be here on the same position. The Jupiter, it's in 6 years, because it takes 12 years to complete one revolution, rotation about the sun. So it will be 6 by 12 multiplied 6 is become 180 degree angle. So the Jupiter which was here, after 6 years, it will be here. It has moved 180 degrees. And about the Saturn, it takes 29 years to complete one rotation around the sun. So in 6 years, it will be 6 by 29 multiplied 360, and that will be 74.4. So I will, with the help of the compass, I will check where is the 74 angle. From here, I will start. 74 is here. So the Saturn will be here somewhere. It's a little tricky question. So that was question number, my dear students, question number 2, a little tricky. So, my dear students, question number 2 is marking scheme is showing up on your screen. What you can do, you can pause the video and you can take your time, read this marking scheme carefully, and check my answers also, whether I have written the right answers. You can always write a better answer. You can discuss it with your teacher. You can write a much more better answers. Okay, so we are going to the next question. That is question number 3. He says the table 3.1 lists some of the planets in the solar system and their average distance from the sun. Complete the table 3.1 by writing in the names of the missing planets. Okay, so remember that word, what we say, my very educated mother just served us nachos. Okay, so Mercury, then we will have here Venus, Earth, and then you will have Mars, and then you will have Jupiter. So this is how this will be done. So remember these code words, and it's a very important thing to memorize them. My very educated mother just served us nachos. So you will have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. So these are the two names which you have to write: Venus and Mars. So this is how you do this question. Then question number 3, B part, he says, as the planets move around the sun, the distance between Earth and Jupiter changes. Use the table 3.1 to calculate the smallest distance and the largest distance between the Earth and the Jupiter. So Earth and the Jupiter, the smallest distance between the Earth and the Jupiter will be when the Earth and the Jupiter, they both are on the same side of the sun. And the largest distance between the Earth and the Jupiter is when the Earth and the Jupiter is on the opposite sides of the sun. Okay, so when they are on the same side, the distance between Earth and Jupiter will be the difference of their radius, their orbital radius. And when they are on the opposite sides of the sun, then the distance between the Earth and the Jupiter will be the sum of their orbital radius. They are given here. Okay, so let me show you how this is done. Okay, so the smallest distance will be when the Jupiter and the Earth, they will be on the same side of the sun. So the distance between Earth and Jupiter will be the radius of the orbit of the Jupiter minus the radius of the Earth orbit. So it will be 7.8 expo 8 minus 1.5 expo 8. So I will take expo 8 common. So in the bracket, you will have 7.8 minus 1.5, which will be 6.3 expo 8. 6.3 expo 8 is the smallest distance between the Jupiter and the Earth. Then they have asked us to find the largest distance between the Jupiter and the Earth. The largest distance between the Jupiter and the Earth will be when the Earth and the Jupiter are on the opposite sides of the sun. In that case, the distance between the Jupiter and the Earth will be the sum of their orbital radius. So it will be 7.8 expo 8 plus 1.5 expo 8. Expo 8 will be common. So in the bracket, you will have 7.8 plus 1.5, which will be 9.3. So the answer will be 9.3 expo 8 kilometer. So 9.3 expo 8 kilometers. So then we have question number 3, C part. He says, A planet is in orbit around a distant star. As it passes in front of the star, it blocks some of the light of the star from reaching the Earth, reducing uh, the brightness of the star as uh, as seen from the Earth. Figure 3.1 shows the view from Earth as the planet passes in of the front of the the star. Okay, so figure 3.2 shows an incomplete graph of how the brightness of the star varies with the time as seen from the Earth. The planet is in front of the star from T1 to T2. So when the planet will come in front of the star, it means that the planet will be between the sun and the earth. The planet comes between the earth and the sun. So what happens, the planet will block some of the light of the sun, and obviously it cannot block all the light of the star. So it will be not total dark when the planet is between the star and the earth, but some of the light is blocked. Okay, so the light intensity will drop, and then for some time it will become, for a very minute time, for a short time it will become constant, and then again the brightness will start increasing when the planet will come between the star and okay, so here we go. So we have so here we have let me show you. He says the planet is in front of the star from T1 to T2. Here we on the y-axis we have the brightness of the star as seen from the Earth, and here we have time. So T1, the planet will come between the, it will start coming between the star and the Earth, and at T2 it will be done. So complete the figure 3.2 to show how the brightness of a star varies with the time. So the brightness of the star as T1, the star comes between the the planet comes between the star and the Earth. So the brightness will drop, then the brightness will become constant. It will not go down to zero. The brightness of the star which is seen on the Earth, that will not go to the zero. Okay. So then again it will start rising, and then again it will become normal as before T1. So this is the graph which you have to draw. Okay. Then he says, describe how the completed figure 3.2 should be changed to show a larger planet passing at the same distance in front of the same star. Okay. So if the planet which comes between the star and the Earth, if its size is larger, what will happen? Okay. So when a larger planet will come between the star and the Earth, there will be less brightness when the star will be blocked by a larger planet. Flat section of that graph between T1 and T2 will be at a lower level because less brightness will be there. Flat section will be for a shorter time. The flat section will be for a shorter time. So, that is question number 3C. Second part, we will check his marking scheme as well. But okay, let's go to the next part. He says, suggest how an astronomer use the changes in the brightness of the star to measure the orbital speed period of the planet around the star. So how they will find some 1 mark question. So when you see what they will do, they will start counting the time when the brightness started decreasing, and they will wait until this brightness again starts to drop. Okay, for example, at T1 the brightness started decreasing, so they will start noting down the time from that moment until again the brightness starts decreasing. So that will be the required time. Okay. So measure the time from T1 to the next time when the brightness starts to reduce. So that was the question. So just how an astronomer uses the changes in the brightness of the star to measure the orbital period, means in how much time that planet will do one orbit around the sun. So we are done with the question number 3. So marking scheme of the question number 3 is showing up. Okay. So let's check if our answer is right. Smallest distance is 6 point. I'm not sure. What is the smallest distance? So we have 6.3, not here, 6.3 and 9.3. Let's check. I'm just checking the answer. Lower brightness when light is blocked, the flat section at a lower level. Time to reduce brightness, time to increase brightness is longer. Flat section of for a shorter time. Okay. So these are the answer. You can see the marking scheme. My dear students, you can pause the video. You can take your time with this marking scheme. So we are on question number 4. Okay, so my dear students, we are on the question number, 4. When astronomers look at distant galaxies, they find that the frequency of the light from the galaxy is shifted towards the red end of the spectrum. Apart from visible light, state two types of electromagnetic waves that contain most of the energy emitted by a stable star. Most of the energy emitted by the stable star is infrared, visible light, and ultraviolet. So the visible light he has already named. The other two will be infrared and ultraviolet. Infrared and the ultraviolet. Question number 4a, second part, he says, describe what is meant by the red end of the spectrum. Red end of the spectrum is that part of the spectrum where the electromagnetic waves or the rays they have, or radiations, or you can say light, that has very low frequency, and the wavelength of those waves is very large. It is the part of spectrum that has lowest frequency and largest wavelength. Question number 4 is B part. The speed of recession of a galaxy is the speed at which the galaxy is moving away from Earth. All the galaxies, they are going away, they are moving away from the Earth. Astronomers use redshift to measure the speed of recession. Astronomers can also measure the distance d of the galaxy from Earth. Such large distances are measured in light years. Astronomers can estimate the time, capital T, that the galaxy has been moving away from Earth using the equation. T is equals to capital D, that's the time the galaxy is moving away, and that is equals to D divided by the speed of recession. Table 4.1 shows their estimate for 4 different galaxies. So light years, D in light years, so that is 4 point, that is distance actually. 4.9 expo 7 light years, 1 expo 8 light years, 3.2 expo 8 light years, 3.9 expo 8 light years. The speed of the recession of each galaxy is given 1100 kilometer, 2400 kilometer, 6700 kilometer, and 9000 kilometer per second. And the time will be, so that shows the time of recession. It means the time it is going away. For the galaxy number 1, it is 13 billion years. And for galaxy 2, it is 13 billion of years. And for galaxy number 3, it is 14 billion years. And for galaxy number 4, it is 13 billion years. State what is meant by a galaxy. You see, the galaxy is a collection of dust and gases and millions and billions of stars. So let me show you. Galaxy is a system. Galaxy is a system of millions or billions of stars together with gas and dust held together by gravitational attraction. Okay, so that is what is meant by galaxy. He says show that 1 light year is equal to 5.9 expo 15 meter. Okay, so the light year means it's the unit of distance, and this is the distance traveled by light in 1 year. You know the distance is speed multiplied time. Speed is 3 expo 8 meter per second, and the time in 1 year is, you have to take the time in seconds, so it will be 365. There are 365 days, multiply 24 because in 1 day there are 24 hours, multiply 3600 because in each hour there are 3600 seconds. You just do this calculation, you will get this number. So here we go. So it will be 3 expo 8 multiply 365 multiply 24 multiply 3600, and you will get 9.5 expo 15 meter. Okay, so we have next question. This is question number 4. And then we have describe the relationship between the speed of recession and its distance from the Earth. You see, the more the galaxy is away from the Earth, the more the distance between the galaxy and the Earth, the, the faster is its speed of recession. The faster is its speed of, greater the distance from Earth, greater is the speed of recession of the galaxy. Okay. Then the fourth part is, he says, explain how the values of the capital T provide evidence for the Big Bang theory of the origin of the universe. You see, the time you see for each planet, sorry, I said planet, for each galaxy, look at this time of recession. This is the time which we think that it has been going away from the Earth. So if you look at the time, for all the galaxies, it is almost 13-14 billion years. So it means that for the last 13-14 billion years, they are going away from each other. So that means 13-14 billion years ago, they were together with each other. So that is evidence which support the Big Bang theory, according to which the everything was together in the start, and then a big explosion happened and all the galaxies were formed. It happened like 13-14 billion years ago, and from that table I can show you that all the galaxies have almost the same time. Value of the T are nearly same for all the galaxies. All galaxies were together 13-14 billion years ago. So that is a proof for the Big Bang theory. Okay, so I think we are done with the question number 4. Let me bring the marking scheme. Okay, so this is marking scheme. I can. So, okay, so the question number 4. Yeah, now we have this question number 4. It's marking scheme is showing up on your screen, and if you want more time with this marking scheme, you can pause the video and you can take your time with this marking scheme. And you know, it's very important. Whenever I solve a question, I always check its answer. I compare it with the marking scheme. It's a very important thing. So you can look at the marking scheme and you can correct my answers. You can also write better answers than me. Okay. So now we are going to the question number 5. He says the sun produces energy from nuclei of hydrogen. Hydrogen nuclei are positively charged. Describe the process that produces this energy. You see, the process which is happening in which the hydrogen nuclei come close to each other, and this is called nuclear fusion. And because in this, the smaller nuclei fuse, hydrogen nuclei fuse into each other, and they make helium nuclei. And this is fusion process, and this produces enormous amount of energy. Okay. So hydrogen nuclei fuse together to form helium. This process produces large amount of energy. Okay. Question number 5A, second part. Explain why this process needs high temperature to occur. You see, the nucleus of hydrogen and the other nucleus of hydrogen, they both are positively charged. And they repel each other with a very strong force. And to overcome that repulsive force, we need a high temperature, high temperature. So when the temperature is high, then they fuse into each other, because then they have enough energy that they can overcome the repulsive force between the between the positive and positive nucleus of hydrogen. They can overcome the electrostatic force of repulsion. Hydrogen nuclei are positively charged. When they come close to each other, they have very strong force of repulsion. To overcome this repulsive force, very high temperature is required. Okay. Then we have question number 5. It's B part. He says, some stars are initially much more massive than the sun. Describe the life cycle of such a star after it has passed through the stage of being a protostar. So the B part of the question 5, some stars are initially much more massive than the sun. Describe the life cycle of such a star. We are talking about a star which is more massive than our sun after it has passed through the stage of being a protostar. Okay. So after being on the stage of the protostar, this is just so so this is massive to have stellar nebula. That's the start. Then you have a massive star, for example, and then that will convert after the protostar. It becomes a main sequence star that converts into the red supergiant, and then the supernova happens. Then either a neutron star is formed or a black hole is formed. Okay, so I just want to read this so you have a much more clear vision. I have also written this answer. Nuclear reaction at the center or core of a star provides energy which makes it shine brightly. This stage is called the main sequence. The exact lifetime, sorry, so that after the protostar, this thing becomes okay. So if you want me to start from the start, all stars form in nebula, which are huge clouds of gas and dust. Though they shine for many thousands and even millions of years, stars do not last forever. The changes that occur in a star over time and the final stage of its life depends on a star's size. Okay. The nuclear reaction at the center or core of a star provides energy which makes it shine brightly. This stage is called the main sequence. So after the protostar, it becomes main sequence star. The exact lifetime of a star depends very much on its size. Very massive stars use up their fuel quickly. This means that they may only last a few 100,000 years. Smaller stars use up fuel more slowly, so will shine for several billions of years. Eventually, the hydrogen which powers the nuclear reaction inside a star begins to run out. The star then enters the final phase of its lifetime. All stars will expand, cool, and change color to become a red giant. What happens next depends on how massive the star is. Uh, um, so because the question is on us about the massive stars. So a massive star experiences a much more energetic and violent end. It explodes as a supernova. This scatters materials from inside the star across space. This material can collect in nebula and form the next generation of stars. After the dust clears, a very dense neutron star is left behind. These spin rapidly and can give off streams of radiation known as pulsars. If the star is especially massive, when it explodes, it forms a black hole. So this is because this answer need uh, more uh, because this answer was of 4 marks, and I want you to I just read it from a website that what happens with a massive star. So I have also written here, and I can read my answer also. Main sequence star, the hydrogen nuclei will fuse to form helium nuclei. Every fusion reaction release heat and light, energy which keeps the core hot during the main sequence. So now the star will become from the protostar to main sequence. The star is in equilibrium. Once the hydrogen causing the fuel reaction in the star will begin to run out, helium nuclei will undergo fusion to form beryllium. Stars become red supergiant stars. Once the fusion reaction inside the red supergiant finally finish, the core of the star will collapse suddenly, causing a gigantic explosion. This is called supernova. The neutron star that forms at the center will continue to collapse under the force of gravity until it forms a black hole. So this is my answer. Okay. So and let's have a look at the marking scheme. What the marking scheme, because that answer was only of 4 marks, and I have read that answer from two different sources. So what the marking scheme wants? Marking scheme wants becomes, he says, becomes a main sequence star, which is a stable star, expands to become a red supergiant, and then it says becomes a supernova and throws off outer layers, and core becomes neutron star, or if original mass large enough, core shrinks to become a black hole. So this is my answers. I have written an answer, then I have read an answer from a website, and now I am reading question number 5B, first part, and from the marking scheme. So please write your own answer, and because there was only limited space available to write that answer, 4 marks are available for this. So write a good answer yourself. So, okay, so we are going to the next part. This is question number 5B and its second part. It says, although the early universe contained only light elements such as hydrogen, it now contains a number of very heavy elements. State in which part of the life cycle of a star these very heavy elements are formed. You see, in the stars, first the hydrogen fuses, they make helium, then the helium and helium fuses into each other when the hydrogen is finished. Then the helium and helium fusion starts, that makes beryllium, and the beryllium then fuse into other elements, and in this way the elements fuse into each other and heavier elements are formed. This happens when the supernova takes place. This happens when the supernova is happening in a supernova. So we are done with this, and so my dear students, these example, there were 5 example questions. So my dear students, there were 5 example questions given to us. These were structured questions. They will be in paper 2. This is just an example that this kind of questions, theoretical questions, will come in paper 2. I have tried my best to explain you the concept, not just write the answers, but I have tried to explain the concept, and I have tried my best. I hope this will benefit you. If you find this video useful and interesting, please like this video. Please share the link of this video onto your Facebook, onto your Twitter accounts, because when you do this, this helps me to promote my channel. Share the link of this video with your class fellows, junior students, senior students, with your teachers. I think it's a great blessing for me that I can make these videos which can touch the life of so many students around the globe. Thank you very much. Have a good day. God bless you all.